All right, so in this chapter, we are going to be talking about waves in general. We are going to focus on sound waves with this chapter, and then we will shift our focus to light in the next chapter. But let's get some general information about waves. So first, we're going to talk about something called simple harmonic motion. Here it says that we have vibration about an equilibrium position in which a restoring force is proportional to the displacement from equilibrium. In this image, you see that there is a spring, and ideally this is an animation so you can see it moving, but that's okay. We will pretend that you can see this object oscillating or bouncing to the right and then back to the left, to the right, and then back to the left. And so what we would see if we could see this full animation is this vertical line here in the orange represents the equilibrium or resting position. If my spring is to be compressed so that the spring is actually back here, then we would see that this position arrow would go here. My position would be to the left of equilibrium. And at that same time, we would see that my restoring force would be directed to the right. Now, if we are looking at this equation, F is equal to negative kx, this is known as Hooke's law. And the idea here is that someone or something manipulates the spring so that we move it out of equilibrium. So let's make sure we all understand what equilibrium is. When we say from equilibrium, this is going to be the resting position. Maybe you want to call it the normal position or whatever that neutral position would be. So for our spring, if we were to leave the spring alone and allow it to just rest or allow it to relax, we would find that this equilibrium position is the position that it would stop at, where it would be no longer in motion. This would be its resting position. So that's what we see here with this vertical orange line. Now, it says vibrations about an equilibrium. Well, about an equilibrium position. That's because my box is going to cause this spring to move so that it's actually going to bounce back and forth between the left side and the right side of this equilibrium position. Now, in all sciences, there is this common theme here that if we were to disrupt what is the normal, natural, resting, neutral state of whatever we're discussing, whether it be chemistry, biology, or physics, then the natural response is for whatever we have disrupted to return to the way it's supposed to be, the way it was, to that equilibrium, resting, natural, neutral position. So the same is true here for our spring. If we squish this spring, if we compress the spring, then we have moved it out of its equilibrium position. So this means that it wants to return to equilibrium. So the restoring force is the force that would be responsible for taking it from this position here and moving it back towards equilibrium. So on the illustration or the animation, it had the restoring force up here. So I just kind of drew it where it would be if the animation were live. But on the image, I want you to see that this is the direction of the force because we're trying to get back to this point right here, back to that equilibrium or resting position. And so let's say that my spring is pushed back towards the center. Well, unfortunately for the spring, it is not going to stay in that neutral or resting position. It will exhibit Newton's first law, an object in motion will stay in motion. So once it begins moving, it actually is going to end up overshooting that position, and our poor little box and spring are going to end up over here past equilibrium. So now we would have a displacement in this direction. So now my box has moved to the right of equilibrium position, which means that it once again really wants to get back to that neutral resting place. And so the force acting on it is now going to be to the left And so if this animation were to continue for us or were to play for us, what we would see is that it's just simply going to bounce back and forth, and those arrows are going to be swapping directions repeatedly. So simple harmonic motion is basically repetitive motion. We're going to be looking at springs a little bit more. We're going to look at pendulums, and then we're going to talk a little bit about the particles in a mechanical wave and how they all exhibit this repetitive motion, sometimes called an oscillation. And we can see here with our spring specifically that the restoring force is always back towards the midline, towards that equilibrium position. So it's in the opposite direction of the actual displacement of, in this case, our spring. So you see that the equation is written so that it's a negative kx, and it will be a negative kx because the restoring force is always in the opposite direction of that displacement. Now, if we were to look at a pendulum would be a situation where we have a mass suspended on a spring, or I'm sorry, on a string or a rope or something like that. So what we see in this illustration is that they have noted that our equilibrium position now is right here in that perfectly vertical position. So if we were to allow the mass to just relax, if we were to not mess with it and just leave it alone, come back and check on it tomorrow, we would find that it would finally settle in this perfectly vertical position. So this will be our equilibrium position. Now, if I wanted to move my mass out of this position, then I would grab it and I would want to just simply pull it to the right, or maybe I would want to pull it to the left. But you see, I drew those arrows as linear directional arrows, but since it's a pendulum, it's attached to a string, we need to think back to our circular motion chapter, where we understand that if we pull on it or if it moves because of the tension in that string, it's actually not going to follow a perfectly linear displacement. It's going to experience a curved displacement. So we are going to measure the displacement when we are dealing with pendulums as an angle. Okay, so this angle here would tell me how much it has moved from that equilibrium position. And if we move it to the left, then, we would just simply mark our angle on this side. But in both cases, whether it's the spring or the pendulum, my object is going to move so that it goes from one side past equilibrium across to the other side, past equilibrium across to the other side, and it's just going to continue going back and forth, once again exhibiting that harmonic motion that we talked about in the beginning. So let's put some vocabulary to this image and understand a little bit better the words that we're going to be using moving forward. So amplitude is our first vocabulary word, and it says that this is the maximum displacement from equilibrium. So yes, my pendulum is moving out of that neutral position, but I could have illustrated my pendulum anywhere along this moment of its motion. However, if we are talking about the amplitude, those places would not be valid options. Notice that it says it is the maximum displacement. So it would be the highest or farthest that we moved it from that equilibrium position. So either of these locations to the right or to the left would be appropriate for our amplitude. And once again, it is being measured from equilibrium. So this angle here was what we would measure, not all the way across. Okay? All right, the next word is period. So period is a vocabulary word that we have addressed before, and this is a period of time. So when we start doing our math work, this is going to be a capital T for period. We are wanting to continue to measure that in seconds, and we are, in this case, specifically timing one complete cycle of motion. So sometimes you are going to hear the words, you might hear vibration, oscillation, cycle, wave, wave cycle. All of these are synonymous with each other. It's basically allowing the object to go one time through the complete pattern of its motion. So if we were wanting to find the period of this pendulum, we would need to allow our pendulum. Now, we're not going to start from equilibrium. We're going to disrupt it from equilibrium. So let's say that I physically raise it up to this point right here. I have to allow my pendulum to swing all the way to the right. And then if I only allowed it to go here and then stop my timer, I actually have not allowed it to complete its pattern, because the pendulum is going to return, right? It's going to go back the other direction. So I have to allow my pendulum to swing all the way back to the left. And once it returns to this side of its swing, now it has completed its pattern. So for our pendulum, we could say that it swings to the right and returns to the left, right? So we have to allow it to return to that starting position where we began our timer. Once it returns to the left-hand side, then we would stop our timer. That would be one complete wave cycle. And so now we would have the period. One time through its motion is all we're timing for the period. The frequency is going to represent the number of cycles or vibrations per unit of time. So we are going to use the lowercase f for our frequency, and we are going to be counting for only 1 second of time. So it says the number of cycles per unit of time, and so we are going to want to keep our time in seconds. So we sometimes see that frequency is measured in a unit of 1/seconds, because there is no unit of measurement for cycles. We're just counting the number of occurrences. Sometimes we will see this written as seconds to the -1. But what I need you to know as the unit for frequency is this unit hertz, and we're going to abbreviate that with the capital H, lowercase z. So 1/seconds, seconds to the -1 power, or hertz are all acceptable units for frequency, but we will most often see it written as hertz. Now, if we cannot, or maybe we do not wish to, actually have our pendulum go through its motion, but we want to calculate what the period would be for our pendulum, then we would use this equation right here. T equals 2 pi times the square root of L/G, where T, once again, is the period, and we are going to want this to be measured in seconds. L is going to be the length of the string, cable, wire, whatever it is that our mass is suspended on, and so we will want that to be in meters. And then G, you can see here, it says is the free fall acceleration. So this is going to be our acceleration due to gravity, measured in meters per second squared. If we are on Earth, we will use 9.8. We are not using a -9.8. Period is time. This is scalar. It is not a vector quantity. We are also taking the square root of this value, and we cannot square root a negative number. So please make sure when you do your math work that you input just the magnitude of our gravity here of 9.8. Obviously, if our pendulum is not on Earth, then we would need to substitute in the appropriate gravitational rate. Looking back at our springs again, if this is a spring, and this is honestly not any different than the spring that we were looking at on the first slide, except that on the first slide, our spring was drawn so that it was moving horizontally. Here, our spring is oriented vertically, so instead of someone or something having to come and manually compress that spring on the first slide to put it into motion, we could simply hang this mass. The weight of the mass is going to then act as the force that puts our spring into motion, and then it would oscillate from there. So our vocabulary words are the same. Amplitude is the maximum displacement from equilibrium. So we identified equilibrium on the horizontal spring. Let me just show you really quickly what it would look like here. Let's assume that this was the resting position of my spring. If my spring were to be compressed so that the box was here, then this would be my highest or my compressed location. And if it were to stretch out so that my box was here, because of the force attached to it, then this would be my lowest position. And if I drew this accurately, came pretty close, what I would find is that my displacement, whether I'm measuring on the side above equilibrium or I'm measuring on the side below equilibrium, both of these displacements should be the same because it's going to oscillate so that it's exactly the same displacement out of position, both in front of or behind equilibrium, above or below equilibrium. If we want to think of these as being directional, or if we were looking at a graph and we were graphing their positions, this would be the positive and that would be the negative sides of equilibrium, but they would be equal in magnitude. Okay, so amplitude is going to be the greatest or maximum displacement from equilibrium. Once again, our period is going to be a period of time in seconds for only one complete cycle. So we would choose where we're starting to observe the spring's motion, and we would allow it to go all the way through its motion and return to that spot. Frequency is still going to be the number of oscillations per second measured in hertz. And if we wanted to calculate the period without having to observe the spring, then we would use this equation. It looks very similar, but it is not the same formula. This is going to be the period for a spring, and you can see that our variables are slightly different. This is T equals 2 pi times the square root of m over k, where m is going to be the mass of our object that is causing the spring to oscillate. So in this case, it would be our hanging mass, and that will continue to be measured in kilograms. And then K, if you recall, is the spring constant that we learned in a previous chapter, and this is going to be measured in newtons per meter. All right, if we look at this image of the water over here on the right, we can see that something has been dropped into the water, which has caused it to experience the ripple effect. And I want to point out here that these waves that are created as a result of the disturbance from whatever was dropped into the water, these waves are moving out in a circular pattern. And all I want to say right now is that you need to remember that in real life, motion is three-dimensional in many cases, right? So when we are talking about this idea of a wave and disrupting or disturbing or sending a wave out, I want you to remember this image and that it moves out in all directions, okay? So here we have another vocabulary word. Medium is a vocabulary word that refers to the material through which a disturbance travels. So as we continue to talk about waves moving forward, we're going to talk about waves that require a medium and waves that do not. Right now, we are focusing on mechanical waves, which are waves that do not exist if there are no atoms, particles, matter, or material in general for the wave to move through. So we're going to be focusing on the material and what kind of material, what kind of atoms, in order to analyze our wave motion in the future. So medium, material, atoms, particles, matter, okay? Mechanical waves require a medium. We are going to be focusing on sound in this chapter, and sound would be an example of a mechanical wave because it does require a medium. So it says here, sound does not travel through outer space. There is no matter. There are no atoms in outer space. So we would not be able to hear anything. There would be no sound created because there are no molecules to vibrate or to oscillate in order to create that sound. Okay, so make sure you understand we need a medium in order to create sound. I need you to know the difference between a pulse wave and a periodic wave. So a pulse wave is a single one-time disturbance. A periodic wave is going to be a continuous wave. So periodic wave, it says a wave whose source is some periodic motion. Here it says constant motion. I like to use the word continuous. A sine wave, so a sine function in math class is a wave that looks something like this. And so very quickly, this is not a math lesson, but let me just very briefly review this with you. A sine function is going to create a pattern on a graph so that we have these alternating highs and lows. If we were evaluating the value on our y-axis, we would find that it alternates between some positive y value and some negative y value. And what we should find, my drawing is a little off here, what we should find is that the oscillation or the y value difference here from equilibrium to the highest point and equilibrium to the lowest point would be the same. Okay, so as we mentioned before with the oscillating pendulum, with the oscillating springs, it moves the same distance on both sides of equilibrium. For our sine graph, we would see the same displacement on both the positive y and the negative y side. All right, there are some shapes that you need to know for waves here. Transverse waves are waves whose particles vibrate perpendicular to the direction of the wave. So if this animation were live, what we would see is that my slinky gets moved upward. So these coils of the slinky move up, and these stay in their relaxed state. As the energy, and I want to make sure you guys know it is the energy that moves along the slinky. As the energy moves through the slinky, these coils individually do not relocate. The coils that the hand is holding never leave the hand. But what happens is that these particles will return to their position, and now the particles that have been disrupted would be located at a different place on the slinky, and so we end up getting that wave ripple effect, okay? With a longitudinal wave, the oscillations or the disruption is going to be along the same line as our energy motion. So here, the person pushed the slinky forward so that it basically squished this little section of the slinky. And so what that did was it created a space of compressed slinky coils. Now, once again, the energy is what is going to move across the slinky. The coils themselves are not going to relocate, but if we were able to watch this as time goes by, what we would see is that these slinky coils would return to their normal spacing, and then we would have a section of compressed coils at a different location along the slinky, and then it would just kind of continue like that, moving that compressed or squish section of the slinky along the line. So a transverse wave, transverse with a capital T, has the particles vibrate perpendicular. There's our symbol for perpendicular to the direction of the wave. So the particles are oscillating up and down, whereas the energy is moving horizontally. Longitudinal wave, a wave whose particles vibrate parallel. So the direction of the motion and the direction of the energy are parallel lines to each other. So parallel for our longitudinal. Okay, so there's our L's for parallel and our L's for longitudinal. For the parts of our wave, we are going to just add some detail to the amplitude definition that we already had before. So we said amplitude is the maximum displacement from equilibrium. If we are looking at a transverse wave, if we were to put our equilibrium line, it'd be somewhere along here. So if we measured our amplitude on the positive side, then we would call that location of the greatest positive displacement our crest. And if we were to measure our amplitude on the negative side, then we would call the location of that negative amplitude the trough. And both of these are going to be locations of maximum displacement. We just give a specific name for the highs and the lows. Notice that amplitude is only measured from the midline, okay? And then it says wavelength is the distance between two adjacent similar points of a wave. So basically, when I was saying earlier that we have to allow our object, whatever it is that's oscillating, to continue one complete pattern, wherever on our wave we want to begin measuring the wavelength, we simply have to allow our wave to complete its pattern. So if we wanted to measure the wavelength here, we could measure how far it is from this crest to the very next crest, because that would have allowed it to go one complete time through its pattern. Maybe I choose to begin my measurement right here as my wave crosses from positive displacement to negative displacement on my graph. So if I were to begin my measurement here, I would have to allow it to continue all the way through the negative phase, all the way through the positive phase, and then I would end my measurement when it returned here, and this would be one complete wavelength, okay? So wavelength is a variable that we are going to use in future calculations. So there is our symbol, it's the Greek letter lambda, and it is a length, so we are going to continue to measure that in meters. Now down here we have an image of a longitudinal wave. So the longitudinal wave, I don't have it typed out for you, but that's okay. We're going to analyze it right now anyway. For our longitudinal wave, we have areas where the waves are spread out pretty good, and then we have areas where our particles, or in this case our slinky, is really tightly packed in, where they're really squished together. So these are the two different phases. Instead of having a positive and negative amplitude or an up-down phase, what we're going to have is what we call compression. We're going to have our compression phase, which is where these particles are really dense. They are squished together, really tightly packed in. And then we are going to have our rarefaction phase. And this is where our particles are less dense. They are spread out a little bit more. So we can still measure a wavelength with our longitudinal wave. Same as before, just wherever you decide to begin your measurement or observation of the wave, you have to allow it to go through both phases of that wave cycle, and then you can mark your wavelength. We're going to calculate the speed of a wave by using this formula, V equals F lambda, where V is my velocity measured in meters per second. Lambda is my wavelength measured in meters. Frequency is the F measured in hertz. And remember, a hertz is the same thing as 1/seconds. So when we multiply that across, we do indeed get meters per second. The wave speed is going to vary with the medium or the type of material or particles that it's moving through, and we'll address that again at a later note. Wave interference is where we have more than one wave that come together and they basically pile on top of each other, for lack of a more scientific explanation here. So constructive interference is where we have two waves that are going to be on the same side of equilibrium. So if we think of the root word constructive, construct means to build. So if we had two waves that both had positive amplitudes, and they joined together so that they perfectly met up or stacked up on top of each other, they would indeed give us a larger amplitude. And so that's what we get with constructive interference. So if this was a positive one and that was a positive one for my amplitude, then they would join together to give me a +2 amplitude. If I have destructive interference, now I have waves that are on opposite sides of equilibrium. So if I have one positive wave and it's going to meet up with one negative wave, and they're going to join up so that they are perfectly stacked together. Well, now one just kind of fills in the other, right? If this is a positive one and this is a negative one, they're going to come together for 0, no amplitude, and that's what we see here in this example. Now, they will not always come out to be 0 if one is larger than the other. So if that's a positive one and then it meets up with a -2, then when they join up, we would have my positive one and we would have my -2. So this positive one is going to fill in some of that hole, but I would still be left with a bit of a gap there, right? So I would get a -1 as the result of those two waves combining. And I just want to back up and make sure you guys understand constructive interference can also take place with negative amplitudes as well. So if we had two negatives that joined up, oh, I said negatives and I wrote positives, sorry about that. If I had two negatives that joined up, then they would just meet up for a larger negative, and that would also be considered constructive interference. If we have interference of two waves that are very close in frequency but slightly different, instead of them joining up so that they are perfectly in phase with each other, sometimes what we get is two waves that are slightly offline. And so as a result of that, we're going to have some variation in how they constructively and destructively interfere. And so basically, I just need you to understand whenever we have two waves that are really close to the same frequency but slightly different, we're going to calculate what their beat frequency is by taking the absolute value of the difference between those two frequencies. So it doesn't matter which one you add. Which one you put in your subtraction first, as long as you find the difference of the two, and we're always going to express that as